So how energy-based models work is we have real images that are from the training data set, and the model itself is going to generate fake images that look as close as possible or try to look as close as possible to a real image. And so they're going to try to, when we say real image, they're going to try to create these fake images that look like real images. And so that's why their energy scores for these real images, they're going to try to minimize those energy scores. Because for real images, the energy score is low. So when they're creating these fake images, they're going to try to minimize the energy scores. They're going to adjust the pixel by pixel of the image. They're going to nudge each pixel, nudge the image such that the energy of that image is minimized, such that it looks like a real image. And so now we have a positive image and we have a negative image. The positive image is the real image from the training set, and the negative image is the fake image that the model generated that looks like that looks like a real image. And so we have these positive negative pairs. So this framework is similar to contrastive learning in the sense that we have these positive negative pairs, and the model does learns by trying to pull the negative pairs, negative examples away from the positive examples, and to score them in directionally opposite, in opposite directions. So we want to score these positive examples, these real images, to have a low energy, and then these fake images to have a high energy, score. And so what we do is, let's say we have a batch, and in this batch we create these fake images, and we run this through a neural net, and we try to adjust the weights such that higher energy scores are associated with the fake images, and low energy scores are associated with real images. And so this is sort of an adversarial serial approach here, where we create these fake examples that look real, and we update the weight such that those fakes have high scores. So we're trying when we're creating these fakes, going from random noise to an image that looks real. So we're going to try to get to a low energy score. But then when we're updating the weights during training, we want to ensure that those fakes that we created, that the model has created, now actually have high scores. So initially, as training progresses, we're getting better at producing those fakes that look like real images. And so we repeat this, and then at generation we get to random noise, and now our generation process is so good that it looks very close to a real image. So we go through random noise, and we're going to adjust the pixels, pixel by pixel of the entire image until we get to an extremely low energy score. Diffusion models, right? We have a noisy image, XTT, and we have this diffusion process that we add Gaussian noise at each step. And we can just skip. We don't need to add noise at every step because it's a linear process. We can just skip, right? Adding normal distributions is the same as multiple times just adding a single normal distribution, right? The sum of normal variables is a normal variable. So because of that, we can just add all of the noise at once. So we get XTT, and then the model is going to predict what is the added noise from the original image. What is the added noise? So it's going to predict, okay, X1, so we have X950. This is randomly sampled X950. And at time step 50, what is the noise that is added from X0, from the original image? That's what it's going to try to predict diffusion models. And so we have, let's say, 1,000 time steps. This can vary, and let's say we have 256 images. So we randomly select these images, and we randomly select at what time step do we want the noise to be added. And so the model is going to learn that at these lower noise steps, let's say noise step 1, it's only going to be a little small amount of noise, but I'd say time step 1,000, it's going to be essentially almost pure random Gaussian noise. So depending on the level of the noise, it's going to understand how much noise and predict how much noise is actually added to the image. So if we have, let's say, 100 million images, our batch size is 250. Every epoch we have 100 million over 256 creating updates. One epoch is one pass over the data set. And then at generation phase, when we go to generation phase, then we start with the random Gaussian noise, so X 1000. We predict what noise was added, from the original image, or whatever estimated original image is, what's the noise that is added, and then we use this reverse diffusion equation to get now we know what the entire noise added was. Now what do we think the noise added from X99 to 1000 is? So then we remove that image incrementally. We remove that noise incrementally. So we go from X 1000, remove some noise, get to X99, then we predict what noise from X99 to X0, then we do the reverse diffusion equation to get to X99 to X98, and so on until we finally get to the original image. So we finally denoise these 10,000 denoising steps till we get to the original image. GANs, how do GANs work? So yeah, let's go to energy-based models. So two things for energy-based models is we have gradient update and we have replay buffer. So gradient update is instead of randomly just adjusting the pixels just that we want to lower energy, right? We have this process where we do take the gradient of the energy and then we apply that update to the pixels. Instead of just randomly adjusting these pixels, we have a systematic way of saying, okay, this is the gradient, and then we're going to adjust the pixels by this gradient such that it moves in the direction of the energy landscape, right? Minimizing, we want to get to the valley of the energy landscape, right? Minimize the loss. And so that's a systematic way of getting to the global minima and make sure it doesn't get stuck in the local minima. And so we also add this sort of random noise when we do this gradient update to make sure that it doesn't get stuck in a local minima. And so we do this gradient update systematic way of actually doing of generating the fake image, and then we have this replay buffer saying that, okay, we don't want to just start from random noise every single time, because what happens when you start from random noise every single time and you only do, let's say, 60 steps, so you get a very unrefined image. And what I mean is 60 steps of you do the adjustment of the pixels, right? And 60 steps, it's going to lead to a very unrefined image. So what we do is we take a previous unrefined image and use that as a starting point. And then layer upon the additional 60 steps. So now what we get is we get a more refined image. Right? We get a more refined image. So it's a better fake, essentially, right? That's what it is. It's a better fake. It's a fake image that looks more close to a real image. So that's what we get with replay buffer. When we look at K, right, when we do the entire grading update and we do the nudging the pixels, right, incrementally, right, that itself, that the number of steps that is 60, right, that stays the same. But what changes is where you start and you apply those steps. Right? And then we talk about diffusion models. GANs, how GANs work is we have a generator, discriminator. Generator goes from latent space to create this fake image. And these don't have to be the same dimension, right? Latent space can be some typically smaller dimension, and we go try to learn this mapping from the latent space to this fake image. Generator's job is to trick the discriminator. Discriminator's job is to say, I produce probabilities that when it's given a fake image, so the discriminator gets labeled. If it's a fake image, it's going to the probability that's real. It's going to output that as low. If it's a real image, it's going to say it's a high probability. So discriminator's role is to correctly classify fake and real images. Generator's role is to fool the discriminator such that when it produces an image which is fake, it looks as close as possible to a real image. So it produces a fake image, but it wants the discriminator to think that it's a real image. So the generator's loss is trying to maximize the probability that the discriminator thinks that this image is real. And so that's the role of the generator. Trick the discriminator, think that it's a real image. And now as training progresses, now the generator gets better at producing more realistic images. It gets better and better at tricking the discriminator, which then the discriminator is then trained, and then the discriminator is now getting better at identifying real versus fake images. So now as the discriminator gets better, then the generator gets better. As generator gets better, discriminator gets better. So it's in this feedback loop that where as one gets better at its role, it benefits the other as well. Mode collapse occurs when the generator identifies only a subset, only a few images that fool the discriminator. So what it does is now it just samples those images. It just uses those images, and then it can just fool the discriminator. So what it prevents exploration from the entire space that the generator can produce images from, and so it doesn't learn like a broader data space to generate images. It just picks, okay, these are the images that fool the discriminator. We're just going to produce those. Okay, so that fails when we're talking about generalizability and learning more rich feature spaces that images can generate. So how does this training work? Generators trained discriminators are not trained simultaneously at the same time. We phrase the generator, then we train the discriminator. We train the discriminator. Again, discriminator wants to accurately classify the real and fake images. We train the discriminator. Then we update the discriminator's weights. And the discriminator's weights, again, it's going to look at if it's a real image. If it's a real image, wants to maximize the probability that it outputs is real. If it's a fake image, wants to minimize the probability of real. Wants to minimize the probability of real. So that's the loss, and it's going to update the discriminator. Once we've updated the discriminator, freeze the discriminator's weights. We train the generator. Generator is going to generate an image, produce an image, and it's going to feed it back to the discriminator, and it's going to see what's the probability of real. Now, if the probability of real is very high, then that's what we want. If the probability of real is low, then that's not a good thing, and then that's a large loss. Right, large loss, because what's the objective for the generator? To make the discriminator think that this image that it produced, which is fake, is actually real. So we're going to update those weights. Normalizing flow, we go from image to latent space. Again, these are all neural nets. Image to latent space has to have the same number of dimensions because these transformations have to be invertible. So we go from image, we do these transformations step by step. All of these transformations have to be invertible. And so because all of these transformations have to be invertible, we should be able to go back from image to latent space and from a latent space directly back to an image. So it's a 1-to-1 mapping. And this only occurs when both the dimensions are the same. So latent space is 16 by 16. Image also has to be 16 by 16. Because if they're not, some information is lost. Or compressed, so it's not perfectly invertible. That's why we need to have the same dimensions. Then we apply these series of invertible operations to get to the latent space. And then now, what's the goal here? The goal here is to learn a mapping from image to latent space such that the real images, they appear as they're sampled from a normal distribution. So for example, we have this image, and let's say we're doing a 2D normal distribution. We get 0.20, 0.1, right? This looks like it's sampled from a normal distribution because it has a mean of 0, a variance of 1. So most of these latent vectors will have a mean of 0, variance of 1, but not all of them. We want to make sure that the real images look as though that they are sampled from a normal distribution, the latent space for those. And so it's going to update the weights such that the real images look as that they're samples from this normal distribution. So it learns that mapping. And after it learns that mapping, we then, because it's invertible, we can go from latent space. So we randomly sample a vector from the latent space, from the standard normal. And then we're able to apply those exact same invertible operations to then get to our produce and generate an image. And so we're trying to maximize the likelihood during training. What's this likelihood? Probability that the vector comes from a standard normal because we want to make sure that these latent vectors come from a standard normal. That's our output distribution that we're trying to get to. And then how much did this transformation actually stretch or compress the space? We also want to take that into account, because it's not just, okay, what's the probability of this vector comes from a standard normal, but how much did this transformation that we're doing, these invertible operations, how much did they actually transform or stretch and compress the space? We want to retain that information as well. So that's normalizing flow. EBMs, talked about replay buffers, creating updates. And again, replay buffers is about where do you start? Where are you starting from? Are you starting from random noise, or are you starting from a previous negative sample? If you're starting from a previous negative sample, then it's going to make the next fake that you generate look more real, because it is already underwent a refinement process. Now you're adding on to that refinement, right? And then it goes through the steps. It goes through the steps of the entire gradient update process, right? Where we go through update like K1 to K60, K1 to K60 times of adjusting the image to make it look as real as possible. Diffusion models we talked about, and one thing about diffusion models to make sure that you know is when we go during generation, let's say we say, okay, this is the image. It's going to be a pure Gaussian noise, right? As the input first, pure Gaussian noise at time step 1,000. And we want to predict how much noise was added. So what diffusion is going to do is it's going to say, okay, from the original image, we think that this is the amount of noise. This is the predicted noise that is added. Now, we then use the diffusion equation, reverse diffusion equation, to now get to, so what it does is it goes from x 1,000 to x0, then it goes back to x99. Because we don't want to go directly to x0, because we want to make these adjustments that we have very incremental, so that we remove a little bit of noise, and we at each time step. If we remove this entire noise, then it might be we might overshoot something. We might overestimate the amount of noise or underestimate the amount of noise significantly. So that's why we take these little steps: is predict the entire noise that's added, and then try to get to the x999 state, and then so on, and then keep on denoising until we get to our estimated original image. GANs, talk about GANs, generator, discriminator. Generator gets better at producing realistic images. So it's a minimax. Opposing objectives, both have opposing objectives. And then we have generator latent space, right? Generator goes from this latent space to this image, this fake image that looks as close as possible to a real image. That's the goal. And then normalizing flow, the idea is these transformations that you do from the image to the latent space are invertible, so you can go back from random Gaussian noise back to the image. Now go over reinforcement learning. You have state space, action space, reward function. And this reward function, EPA, is going to be, or the play level EPA is going to be reward for the agent. So the agent is going to simulate play-by-play across all drives for the entire game. And this EPA reward will be given to the agent as it takes it's in a state, takes an action, transitions to the next state, and gets a reward. And then at the end of a drive, depending on the result, it gets a reward based upon the terminal outcome. And we simulate this across an entire game. Now, the EPA reward function, so we have a next state function, we have a next state and a reward model. So how do we know in this game state, agent took this action? this is what the next state is going to be, and this is what the reward is going to be. We run it through a model that has state and action as input variables. So state is the game state, and the action are all the different types of runs and passes, as I mentioned, that we can take. And then historically, that state and that action has produced this next state and whatever the EPA expected points added of that next state. Right? So comparing the next state and the prior state. And then we run it through the model, because not every action state and action space will be historically observed. Right? Not every state and action that the agent even may come across will be historically observed, maybe very few samples. So then that's why we use this model. That's why you have to build this model, so we can possibly interpolate between similar states, actions in similar states. So that's a reward function. And we're going to use the difference between, so typical, what does typical EPA use? It uses down distance and yard line. Down distance and line of scrimmage, yard line. They say, what is the expected points added from this play? Now, what this fails to account is, it fails to account for roster talent, fails to account for weather variables, fails to account for momentum in the case of injury status, in the case of rolling in-season performance, or even in-game performance, depending on how certain players are in the game as well. So so for example, EPA for a team with one elite player, one elite QB versus an average QB should be in theory different, but based on current models, since it only focuses on down distance and line of scrimmage, it's the same. But our reward function is going to shape this EPA into a more extensive and more elaborate reward that takes them into account these latent variables and proxies for these latent variables, because we can't directly observe psychological state or even mental state. So that's why we have these proxies. So for fatigue, we have snap count. For momentum, or for talent, we have season statistics, or rolling in game performance, or for momentum. We also have this recent play sequence that we will also add to try to capture the trajectory that the coach may want the plays to develop in, to try to set up something in the future. And we'll stop there.